Okay, welcome to lecture. We'll get started in just a second. We're continuing on with chapter 16, where we left off, which I think is right around here. So I think in chapter 16, we stopped with talking about pH and calculating pH. So I think we did the example right before this one. And like usual, again, if you have questions, please feel free to ask them in the chat and we'll get back to you. But again, we're going to pick up here and probably finish chapter 16 and roll into 17. 17's notes were just put up online. You'll find them by the final review type area if you need them in Canvas. All right, so we were talking chapter 16, which is acid and bases, and I believe last time we got into some calculations that involve acid and bases. We talked about the idea of Kw, which equals the concentration of H plus times the concentration of OH minus, and that equals 1 times 10 to minus 14. That is a constant. You always have that sort of available to you. It'll allow you to figure out the H plus concentration or the OH minus concentration. Remember that the H plus concentration is the same thing as H3O plus, and again, in formulas and also equations, you'll sometimes see them sort of interchangeable. We also talked about the pH scale, which goes from 0 to 18, above 7 being basic, below 7 being acidic, and technically speaking, at 7 there would be neutral. And we talked about that because pretty much when the H plus concentration equals the OH minus concentration, they both will have a value of 1 times 10 to the minus 7, which means if you put it into the pH equation, which is minus the log of the H plus concentration, you will get a pH of 7 at that point, which again is why we consider 7 neutral. So for our class, we'll just keep it like that. 7 on the nose is neutral. If it is not 7 on the nose, then it is either slightly acidic or slightly basic. But technically speaking, neutral is 7. Although some people have a little bit of leeway around 7 is considered basically neutral. But we'll just keep it simple. Either it is 7 and it's neutral, or if it's not, then it's either, again, if it's above 7, slightly basic. If it's just below 7, it would be slightly acidic in that case. Remember that also towards the end, you did one calculation where perhaps you did it incorrectly, and there is a similar scale where we do the POH. The POH equals minus the log of the OH minus concentration. And the nice relationship is if you take the pH plus the POH, it equals 14. So that's a nice relationship between everything. Again, if you're given the OH minus concentration, that allows you in certain cases to calculate the POH, and then you can subtract 14 from it and get yourself to the pH in that case. While again, if you have the H plus concentration, you could calculate the pH directly. You could also use Kw again to figure out the H plus or OH minus concentration and then go into both of them. This is the case where people sometimes will screw up because they will calculate the pH and go, oh, it's below 7, and then calculate the POH and go, oh, it's above 7. And they'll give an answer like the same solution is both acidic and basic at the same time. Again, because they're looking at both of those values and thinking, oh, one's above 7, one's below 7. So as we talked about last time, again, it does need to be one answer for that. So it's either going to be acidic, basic, or neutral. Again, you can't have the same solution that's going to be all those things together. So you should always, probably always, I would say, look at the pH value because it is the pH scale that most people have in their head. Remember that the POH scale and the pH scale, they run opposites of each other. So if you have a low pH, then you would have a high POH, and vice versa. If you have a high pH, you would have a low POH. So they do run opposites. So it's very common people will kind of do that and give like, oh, it's the, it's acidic and basic together. So again, just one answer for that, either acidic, basic, or neutral. Other important relationships we talked about is sort of the opposite relationship. As the H plus concentration goes up, the OH minus concentration goes down, and vice versa. As the OH minus concentration goes up, the H plus concentration will go down. So there, as one goes up, the other goes down, is sort of the relationship that we see. And that's an important relationship to remember. It is the H plus concentration that's important for the pH. So the larger the H plus concentration, the lower the pH. And obviously opposite would be true. The lower the H plus concentration, that means the more OH minus concentration, and it would be basic. Now the pH scale does increase by a pH of 1 for every times 10 to the whatever power that you go from. So if you had an H plus concentration like in the middle, that's 1 times 10 to the minus 3. If you put that into your pH formula, you will get a pH of 3. If you change it to 1 times 10 to the minus 4, which is basically 1 power of 10 change, the pH will go up by 1 and go to a pH of 4. And if you had 1 times 10 to the minus 5, the pH concentration, the pH would go up as well by 1 power of 10. Pretty much if you have 1 times 10 to the whatever, the pH will be whatever the exponent is. So if you had 1 times 10 to the minus 12, the pH would be 12. If you had 1 times 10 to the minus 9, pH would be 9. But you do need to probably put it into your calculator, obviously, if it's not 1 times 10 to something. So as I mentioned before, as the amount of H plus increases, we would expect a decrease in pH, and lower pH means it is acidic. Remember, as we move from 7 towards 0, it becomes more acidic. As we go from 7 to 14, it becomes more basic in terms of the pH scale. Any questions on any of that stuff there? Now, there are a couple different ways that you can measure pH. Very common way is pH paper, which is what we have on the right-hand side picture. pH paper is pretty much what it sounds like. You take the paper, you dip it in the solution, or you dip the solution onto the paper, and basically the little squares on the paper will change color, and then you basically move it around and try to match it up and go, oh, it kind of looks like this combination of colors, so I think it's a pH of 4, or it looks like this combination of colors is a pH of 3, and so forth. A more sort of accurate, if you will, sort of measurement of pH is done by a pH meter, which is what's on the left. The pH meter is essentially an electrode. It does a little chemical reaction, but basically what it's able to measure is the amount of free H plus in the solution. So those are free H plus ions that are floating around. Remember, that is basically what determines the pH of the solution, is how much of that's around. And as you can see on the display there on the left, it will give you usually a digital display of, hey, the pH is 2.36 in this case, and you will get a digital reading. So these are two very common ways that you could actually measure the pH of a solution. Ways that you can figure out whether or not a solution is acidic or basic, not really measuring pH, but you can use litmus paper. And usually there's red litmus paper and there's blue litmus paper. And red and blue litmus paper, there's also neutral, but usually red or blue is used as well. And you can look for a color change in those papers to indicate whether or not the solution is acidic or basic. Again, it will not tell you what the pH of the solution is, but it will simply just generically sort of tell you, oh, this solution is acidic, this solution is basic. And if we have red litmus paper that goes to blue, that means that it's basic if it turns that red litmus paper blue. And if you have blue litmus paper and it turns red, that means that it is acidic. So again, not a way to measure pH like the two methods on the bottom there, where you could actually sort of get a number to indicate whether or not it's acidic or basic. But you can again use just basic litmus paper, which again comes in red or blue, and looking for a color change will help you indicate whether or not the solution is basic or acidic. Obviously, if the red litmus paper didn't really change color, it's probably still acidic. If the blue litmus paper didn't change color, then it's probably still basic. So if the way to think about litmus paper is blue basic, red acidic, and that's a way, again, just to generically figure out is it acidic or basic, but not necessarily an actual pH value. To do that, you would need one of these two guys, either the pH meter or some type of pH paper. Like if you have a pool or something like that, and you take the paper to check the pH with all that stuff on it, and you kind of swirl it around the pool, that's basically pH paper, and it will change those colors to look at things like the pH, obviously, alkalinity, and so forth on those pool tester type strips. So this is the pH scale, and again, you can see again it runs from 0 to 14, and that's usually what we think about when we think about the pH scale. Technically speaking, and you might even come across a problem on the lab that you technically can end up with a negative pH. It's sometimes referred to as a superacid. It's a very obviously strong acid, but usually we can find sort of the pH scale from 0 to 14. And up on top there, we have sodium hydroxide, which is a strong base, so it's up towards 14. While on the bottom there, towards 0, we have 1 molar hydrochloric acid, which is a strong acid, so we expect that. Things like vinegar, which is like acetic acid, you can see it's at a pH of 3. Lemon juice, stomach acid, which is also hydrochloric acid, those things are also in the acidic range. While things like cleaners, like ammonia, blood, and so forth, they're in the basic range. Pure water is 7. And pure water is 7, and that means that it is neutral. In reality, though, if you took some water from the tap, and you would probably find the pH in this range down here, it would probably actually be acidic. Again, if you kind of just took water, especially if you take water and you kind of just leave it out in the open, and that's because typically tap water, things that aren't really filtered, when you take the water and it's out in the open, it also combines with the carbon dioxide in the atmosphere, and you make something which is known as carbonic acid, which is a weak acid. And what that will essentially do is kind of increase the H plus concentration a little bit, and it will bring your water kind of down in terms of pH. And it sometimes surprises people when they test water, like, I think it should be 7, but actually a lot of times it's more acidic because of that region. And again, especially if it's sort of kept out in the open for a long period of time, it's able to pick that up. And one way, if you want to sort of help out in an experiment where you don't want that effect of having extra H plus because of that CO2 that was basically developed, what sometimes people will do is they'll boil the water, and when they boil the water, basically that will remove the CO2 and just leave you with kind of pure water. And that a lot of times will allow it to bring the pH sort of back up to 7 and so forth. So sometimes when people do like a titration experiment in real life, and they do an actual titration experiment, sometimes they'll actually boil the water before they use it, again, just to eliminate that little excess amount of H plus in the experiment. Sometimes it doesn't make that big of a difference and they won't do it, but sometimes people will do that. So we kind of hit this a few slides earlier, but again, a similar scale to pH is one that measures the OH minus concentration, and that is what is referred to as POH. And again, it's calculated the exact same way as pH. And then really the nice thing about that is it does give you some variety in terms of how you could solve some of these problems. So again, you don't necessarily have to use KW. If you're given the OH minus concentration, you could actually calculate the POH and then simply just calculate the pH by taking 14 minus the POH. And vice versa, if for some reason you wanted to calculate the POH and all you had was the H plus concentration, you could go and get the pH directly and then take 14 minus the pH, and that will give you the POH in that case. So again, this creates sort of a variety of ways you could solve some of these problems. There is not necessarily a better way versus another. Some might be faster, but they all should end up in the same sort of place when you're done, if you do all the calculations sort of correctly. Now let's add a couple of other sort of important formulas to these as well. If you're given the pH, from it, you could actually calculate the H plus concentration. And you do that by taking the inverse log of the minus pH. And on most people's calculators, when you hit the inverse log, that is actually what pops up, that 10 and a caret. And again, to do the inverse log, usually on most people's calculators, that is the shift button or the second button in the top left and the log button. And again, if you have a display calculator, it will pop up that 10 and a caret. Now, you could also, if you're given the POH, do a similar calculation. You could get the OH minus concentration, and that would equal the inverse log of the minus POH. So the minus is important on both of these. You want to make sure you don't forget it. Also going to pop up a 10 and a caret POH. Stuff like that. So this gives you a couple of ways that if you are given the pH or the POH, again, you can get the H plus concentration or OH minus concentration directly from those numbers. Any questions on that there? Okay. So I think we have an example here. So for each of these, why don't you take a minute or two and calculate the pH and the POH for each solution. And while you're at it, determine whether or not it is acidic, basic, or neutral. So take a minute or two, a couple minutes, and then we'll talk about it. It says the inverse log. So that's like second and log on your calculator. If you're asking about what's on top there. So that's the inverse log. It's like the 10 and the caret usually on your calculator. Okay, so let's take a look here and see what we got going on. So for the first one, again, they gave us the H plus concentration, which means we can directly go into our pH equation. And if we just put that in there, that's going to be minus the log of 3.6 times 10 to the minus 9. And that would get us an answer with numbers. 8.44 for our pH. Again, as we also talked about last time, this has two significant figures, which means we do want to take the pH to, again, not two significant figures, but we do want to take it to 2 decimal places. So remember that when we go from concentration to pH or POH or some number like that, the number of significant figures in the concentration is how many decimal places we should have in the answer. Again, not how much significant figures in the pH value. Once we have that, probably the easiest way to get the POH is to just take that the POH would equal 14 minus the pH, and that would get us 14 minus 8.44, and that would give us a 5.56 in terms of our POH. And again, that comes from the relationship that the pH plus the POH equals 14. And again, it's pretty much once you got either the pH or the POH, you pretty much could just subtract 14 from it, and that'll give you the other number that you need. Now, when we're trying to determine is it acidic, basic, or neutral, this again is a place where people will sometimes give multiple answers, which again, if you don't want a big X, don't do that. Yes. So you want to always, in most cases, look at the pH value. And when we look at the pH value, we see that it's 8.44, which means it's above 7. And that means that this first guy here should be basic. Any questions on those calculations there? Now, if we look at our second one there, it's a little bit different. And what's different about it is the information that's given to us. So for number 2, we are not given the H plus concentration, but we're given the OH minus concentration. So in this particular case, it would make sense to first start out with the POH. Hopefully it'll catch up here. Equals minus the log of the OH minus concentration. And that's going to give us minus the log of 9.2 times 10 to the minus 2. And I am getting a little bit of feedback here. So again, hopefully it's not cutting out too badly as we're doing this. So minus the log of 9.2 times 10 to the minus 2 gives us a POH of 1.04. Again, same reasoning in terms of how far we took the POH value. The OH minus concentration was, again, 2 significant figures. So that's going to translate, as we see here, to 2 decimal places. And again, now that we have the POH, we can probably just subtract 14 from it, which is the easier move. So the pH would equal 14 POH. And that's going to give us 14 minus 1.04. And that will get us 12.96. And that would be our pH. Again, when we're trying to determine acidic, basic, or neutral, we want to look at the pH. It's above 8 as well. So again, this guy would be basic. So remember, when you're asked that question, just give one answer. Don't give multiple answers. Any questions on either of those calculations, how we got the numbers, or we did any of that? Sure. What's your question? Yeah, so it's a good question, Grace. And the when you're asked this question, this is what I sort of been talking about. When you're asked the question about the solution, right? So remember, if you have a solution, try to draw it here with my delay. So if you have this solution sitting here in this beaker, for example, right, this solution will either be acidic, basic, or neutral. Yeah? So it will not be all three of those things. It will not be two of those three. It will just be one of those things. That solution sitting in there will either be acidic, basic, or neutral. But that solution sitting in there can have a pH value, also have a pOH value, and which will be different values for the same solution. But regardless if they have different values of pH and pOH, the solution itself can only be one of those three things: acidic, basic, or neutral. And that is why most people, when they think about acidic, basic, or neutral, they think about our 0, 14, and I'll learn to count. 0 on the left there, 7 in the middle, right? Our pH scale, right, which runs like this. And this is acidic, and this is basic. Yeah. Now try to draw a little better on this side. The pOH scale also runs from 0 to 7 to 14. Yeah. And this is the pOH. Okay. Now, on the pOH scale, if it's below 7, it's actually basic because it runs opposite. If it's above 7, it's acidic. So when we look at both of the scales to determine that, when we look at, say, the last one, the pOH was 1. So if you went to the actual pOH scale, that would be here-ish, which tells you it's basic. The pH for that same solution was 12.96, which would be here on the pH scale, which is also basic. So the pH and the pOH will actually tell you the same thing in terms of acidic or basic, but probably 9 times out of 10, people are always thinking of the pH scale. And that's why I said that when you're asked to determine that, you should probably look at the pH scale, because the pH scale is what most people think in their head. And you don't want to look at the pOH because it's actually opposite of that pH scale. So I would recommend just remember the pH scale, 0 to 14, less than 7 is acidic, more than 7 is basic. And then when you're trying to figure out, is it acidic, basic, or neutral, you should look at only the pH value, because that will give you probably what you're thinking about. You could look at the pOH like I did on the right there, on top right, but it does run opposites. And most people don't have that scale sort of in their head. And again, that's a very common mistake that a lot of people will make on these type of questions. Is, like I said before, they very often will do exactly, I think, kind of like what your question was, is very, very common. People will look at this value down here and go, oh, that's less than 7, so it should be acidic. And then they'll look at the other value and go, oh, it's above 7, it should be basic. And then what you end up getting in that case is a solution that's both acidic and basic at the same time, which it can't be. So it's got to be one of those 3 things. Other questions on that? And again, in terms of chapter 17 notes, they are up there. They're by where it says the final exam review material is where you'll find chapter 17 notes if we need them, if we get there today. All right. That was those guys. So let's try this one here where we're actually given the pH and we want to calculate the pOH. So take a second here and calculate the pOH of this solution. Okay, so in this one, we're given the pH, we want the pOH. So this is a perfect one to use the relationship that we saw, that the pH plus the pOH equals 14. And in this case, we're looking for the pOH. So that would be 14 minus the pH. Pen going crazy today. So that's the 14 minus 5.67. And if we do that, we get a pOH of 8.33 for this particular one. So 8.33 is our pOH. And again, here we have a pH and a pOH value. And if we were asked, is the solution acidic, basic, or neutral, we should look at the pH value. And if we look at the pH value, we will see it is 5.67, which means that is less than 7, and this solution should be acidic in that case. Any questions on that one there? Sorry for all the extra lines. It seems like they're having trouble again today. It's like a delay and lines start popping up everywhere. Okay. So why don't you try this one? I'll give you a minute or two here. We have the pH of the solution is 3.14. What is the H plus concentration of this solution? All right, so in this particular case here, we're actually given the pH. And as we talked about earlier, if you're given the pH, you could get directly from it the H plus concentration. It actually tells you in the name, pH will give you the H plus. So the H plus concentration will equal the inverse log of the minus pH. And that means, again, when you put it on your calculator, you hit the inverse log, the second button, and the log. 10 and a caret, you want to make sure you hit the negative, and 3.14 is basically what it will kind of look like on most people's calculators when you do that. And when you get that, you'll get an H plus concentration, if you do a little scientific notation, 7.2 times 10 to the minus 4. It is a concentration, so you should put molarity next to it, which is, again, a unit of concentration, which is typically what you got. Again, on your calculator, may not give it to you in scientific notation. You may get 0.000724436. Again, you don't necessarily have to put in scientific notation. But one thing that you should do is, if we look at our pH value, it has 2 decimal places, which means when we go back to concentration, we should end up with 2 significant figures. So 7.2 times 10 to the minus 4 is 2 significant figures. Again, if you did the decimal, you would want to go 0.00072, and that's how you would want to round it. So just like when we go from concentration to pH or POH, we go from decimal places to significant figures to decimal places. When we go backwards from pH, we want to go from decimal places to significant figures. So 2 sig figs here at the end. From 2 decimal places at the beginning. Any questions on that calculation? And again, may not get in scientific notation on your calculator. You don't necessarily have to do it, and so forth. Yeah, so it says inverse log. So I'll do a very bad drawing here, do my best. On most people's calculator, yeah, probably up here in the top left, you have like a shift button or a second button, something like that. And depending on your calculator, somewhere you have a log button, LOG. And usually above that, it's like a 10 and a caret or a 10 and the X. And then what you would want to do is, again, somewhere you would have your negative button, right? Which looks like that or this, not your subtract button. Yeah. So I'll answer your question about the negative pH in just 1 second. So if you were going to punch this in, what you would want to hit would be, on most people's calculators, if you have a display calculator, you would want to hit that shift button or that second button. You would want to hit the log button. And that usually will pop up like a 10 and a caret on most people's calculators. And then you would hit the negative button, again, not the subtract button. Start with a number. You should do it. So if you have a display calculator, just like we talked about before, you go right in order. You hit the shift, log, negative button, 3.14. If you have a non-display calculator, you would start with the 3.14. You would hit the negative button and then the shift log button. And that should get you pretty much that answer. Again, it won't give it to you necessarily in scientific notation. So you might get the 0.00072. And again, in terms of significant figures, in terms of the answer, we started with 3.14, which is 2 decimal places, which means when we go back to the concentration of H plus, it should have 2 significant figures. So that's why we ended up with 2 significant figures, because of the decimal places. Because remember, when you go the other way, you go from significant figures to decimal places. Then when you go from pH back, you go from decimal places back to significant figures. So if it had 1 decimal place, you technically would take the concentration to 1 significant figure. If it had 3 decimal places, you would take it to 3 significant figures going backwards. Questions on how to punch it in? And to answer the other question, the answer is yes, you could possibly have a negative pH. And that, again, is usually, like I said earlier, involving sort of a superacid, is sometimes called. It's something with it's an acid with a very high concentration, a molarity. And if I'm not mistaken, I think on your post-lab questions for today's lab, there is one that becomes negative, and I think you have one in each question that becomes negative. So it usually is just anything that's basically anytime you have pretty much anything that is a molarity of over 1 per se, you'll probably end up with a negative pH in that particular case, just because it's so large. So usually most of the time we deal with things that are more dilute, so we don't necessarily get above our negative, but you can definitely have it. Won't happen a lot, but it can occur. So, and again, it does occur, I think, on your lab today. So you'll have one that's like maybe 6 molar, 18 molar, or something like that, and you want to calculate the pH for it, and it will end up being a negative number, but on a post lab question. Other questions on that? Okay. Why don't we try another one here just to make sure our calculators work. In this case, you have the POH. What is the OH minus concentration? So see what you come up with. Okay, so basically it's the same calculation. Remember, if you're given the POH, from that you could get the OH minus calculation. And again, we would want to take the inverse log of the minus POH. And again, on most people's calculator, like I said, you got to hit that shift and then the log button. There are some calculators like the one I'm actually using that has a dedicated button for that, but probably most of the time you got to hit that shift in the log. So that's going to give you the and then the caret minus POH, which if we put that in will get us 10 in the caret minus 5.67. And if we do that, we will end up with an OH minus concentration of 2.1 times 10 to the minus 6. Again, we would do molarity here because that is probably the concentration unit. Same idea here in terms of significant figures. The number had 2 decimal places. So our concentration has not 2 decimal places, but 2 significant figures. Any questions on that calculation? By the way, this solution would be actually acidic. And again, that's because if we calculated the pH would equal 14 minus 5.67. Did I say basic? I mean, I didn't think I wrote it backwards there. My bad. Basic. I'll learn acidic or basic. Sorry. There we go. It would be basic, is what I was trying to say. And it is because we take 14 minus 5.7, we get a pH of 8.33, which is basic. It didn't ask for that, but again, it is basic. I think what I was thinking is, again, if you see this number, that's not the pH, that's the POH. Yeah, so that should be the right way to punch it in. The shift plus the log button, and then you want to make sure it's negative, not the subtract button. Otherwise, you'll get in trouble with your calculator. And 3.14. Again, you don't necessarily have to give it in scientific notation. Sometimes it is because there's just oftentimes a lot of zeros involved. Like this particular one would have 5 zeros, so like 0.00000021. You could give it in decimal form if you want, but usually it looks a little bit better. You might not miss a zero or something like that if you do it in scientific notation. It is basic. I apologize. I was looking at the I had it in my head backwards there. Sorry. It is basic because the pH is 8.33. What the reason I wrote acidic, I think, is because I was trying to mention that again, people will sometimes look at this and see it's less than 7, but not realize that it's the pOH. So again, this would be basic in this case, not acidic. Yeah, so this is a basic solution because the pH is 8.33. The OH minus concentration is 2.1 times 10 to the minus 6, which if you, for example, use KW and found the H plus concentration, which again, it didn't ask you to do, just so you can see everything we talked about kind of together. This is KW like we did earlier on in this chapter. And you would get an H plus concentration of 4.8 times 10 to the minus 9 molar, which is a smaller number than our OH minus, right? It's smaller. That means that our OH minus concentration is larger than our H plus, which tells us it's basic. We also see that our pH is greater than 7, which tells us it's basic. So this solution again would be basic. No matter which way you use to determine it, you could use the H plus versus the OH minus concentration like we did earlier. You could use the pH value better than what I did earlier here in this example, and to figure out that it is basic. Any questions on that? Now, sometimes in a lot of cases that we've had up until this point, we've been given sort of a generic, either sort of acid or base. And what I mean by that is they give you here's the H plus concentration, right, which is sort of the acidic. And here's the OH minus concentration, which is the basic. They could actually give you an actual strong acid, for example, or even a strong base. And if they give you a strong acid, what we know about a strong acid is something like hydrochloric acid, when it's in solution, will 100% break apart into H plus and Cl minus. Now, 100% of what we got going on are these ions. And the thing that's really important for pH is really just the H plus concentration. And we know that the pH equals minus the log of the H plus concentration. And when we talked about concentrations, if you remember, if the whole thing is 0.1 molar, it is a 1-to-1 relationship in terms of the H plus concentration. If we're given that acid is a strong acid that you'll get into when you take 1B, you then know the H plus concentration, so you could go into the pH formula and take minus the log of 0.1, and that would give you a pH of 1.00, which is definitely acidic. And we would be able to know that it's a strong acid, so that does make sense. So we have an acidic pH. So if you're actually given a form of an acid or even a base in this case, for example, if I had sodium hydroxide and we had 0.2 molar, what we know about sodium hydroxide, it's a strong base, which means it would break apart into Na plus and OH minus 100. If this whole thing is 0.2 molar, it's a 1-to-1 relationship between that and the hydroxide. The hydroxide is not going to give me the pH, but what it will allow me to do is calculate the pOH first. And if I do that minus the log of 0.2, yeah, I know it's been like that all day. My earlier class was like that as well. It's just not great today. Again, if you need to rewatch something, the good news is it will not be bad on the replay there. So the pOH would be 0.70. And then if we've got the pH from that, it would be 14 minus 0.70, which would give us 13.3, which is definitely a basic pH. So you could do it for a strong acid where you get the H plus concentration. You could do it for a strong base, which would give you the OH minus concentration. And then you could either go into the pH or the pOH one to get to the pH. The 0.1 molar is just an example. If you're asking where that 0.1 molar came from, it's just sort of an example. If you were asked what is the pH of a 0.1 molar hydrochloric acid solution, it's where it came from right here. It was just an example. So again, in our class, if you are given an acid or base and asked to calculate the pH, pretty much going to be a strong acid or base, because like I said before, the weak acid or base is a much longer calculation that we definitely don't get to in here. All right, so why don't you try this one here? Take a second. Okay, so in this case, we are looking for the pH. We're given the concentration of perchloric acid, which, if you remember, is one of those strong acids. So we would have our HClO4, and in solution, it's going to 100% break apart. Give it a sec, it just clicked, so good doing that today. All right, so that we should be back, I hope. We should have the H plus concentration and the ClO4 minus, again in solution. 100% is these guys on the product side. Since we know that this whole thing has a concentration of 0.025, the H plus will also have 0.025 as it's a, wow, nice accent. Sorry about this. There we go. Let's try this again here. Maybe it will calm down. Let's see. pH. will equal minus the log of 0.025. And we get a pH of 1.60, which is acidic. And does make sense since this is an acid. So again, if you're given a strong acid or strong base, you just need to figure out either the H plus concentration for the strong acid and then go into the pH equation, or the OH minus concentration from the strong base and go into the pOH equation. You do want to just be careful. Sometimes a strong base, for example, if you had something like calcium hydroxide and it broke apart, it would give you a calcium plus 2 hydroxides, which means if this guy was 0.1 molar, it's actually a 1 to 2 relationship, which would give you 0.2 molar for your hydroxide, which means in that case, you then would want to go into the pOH, which is the 0.2 molar, because you need to make sure you adjust it correctly. Again, it's a 1 to 2 relationship. So occasionally, more so on the basic side, probably you'll come across that. You probably won't come across that in our class, but you could potentially in the future. You just want to make sure that if it happens to break apart into more than one OH minus or more than one H plus, that you do take that into consideration before you get the H plus or OH minus concentration. Any questions on how to do strong acids, strong bases, calculate the pH? So the last thing we're going to talk about in this chapter here is a buffer. And hopefully the internet here and their site here will hold up for this part. A buffer is a solution that basically will resist changes in pH even if you add more acid or base to it. And there's basically two things that can make up a buffer. Basically, a buffer is made up of either a weak acid and its conjugate base, or is sometimes referred to as the salt of its conjugate base. Or it may be referred to as, are made up of a weak base and its conjugate acid. Or again, the salt of its conjugate acid. So basically, when you have a buffer, and the important part of that is when you have a solution that is a buffer, you have in there together an acid part and a base part actually in that solution floating around at the beginning. And that's really important for how a buffer is able to operate. So you will either have a weak acid with its conjugate base, or you'll have a weak base with its conjugate acid. That difference between those two things, a weak acid and its conjugate base, or a weak base and its conjugate acid, is the same relationship that we talked about earlier on with Bronsted-Lowry. It is 1 H plus difference between those two things, right? So that's one way you could kind of recognize whether or not these two things could be a buffer. They do have to be related to each other by that basic difference of just 1 H plus difference. And it does has to be a weak acid involved or a weak base. You cannot have a buffer that has a strong acid or a strong base. And that is because a weak acid or a weak base is a weak electrolyte, which means that when you have something like acetic acid, which is a weak electrolyte, when it goes into solution, it will break apart into H plus and acetate. And in solution, because it's a weak acid, you actually will have both of these things in there. So that would be like your acid part and your base part would be in there together because it's able to set up that equilibrium basically. So in solution, it's able to have both of those parts in there, the acid part and the base part. If you took something like hydrochloric acid, when it goes into solution, as we've been talking about, breaks apart into H plus and Cl minus. What you have in that solution is 100% these guys, which means the only thing you would have in that solution if you try to make a buffer out of a strong acid or a strong base would be just the conjugate base. So you wouldn't have an acid part in the solution. And again, that's really important for how a buffer works, is the idea that you're able to have both of those parts in there to begin with, an acid part and a base part. Now, what a buffer is a solution that will resist changes in pH. Also, sometimes people think about a buffer wrong in the sense that they think it is a neutral solution. And it could be a neutral solution, but you could also have a buffer that's acidic. You could also have a buffer that's basic. You could have a buffer at any pH that you want. You can make a buffer at any pH you want. The deal is, for example, let's say you made a buffer at a pH of 4. And if you made this buffer at a pH of 4 and you added some base to it, it would still maintain a pH of 4. It would probably go up a little bit. So maybe it goes from like 4 to 4.1, 4.0 something. You know, it stays around that 4. It will not go from like a pH of 4 to a pH of 12 when you add that base to it, because it is able to resist the change. Same thing if you took that buffer that was at a pH of 4 and you added some acid to it, it would maintain about a pH of 4. It would go down maybe a little bit. Maybe it goes down to a pH of, 3.9 or something like that. But it won't go from a pH of 4 all the way down to like a pH of 1. So what a buffer is not necessarily always a neutral solution. But what it means is it will be a solution that whatever the pH of that solution started out as, if you add some strong acid or strong base to it, it will be able to maintain that pH relatively close to each other. It won't move very much. You won't see very big jumps in pH. So let's take a look at sort of how one sort of would work. I'll go back to those slides in just a second. Okay. So when we look at the a buffer, for example, let's add HCl to water. Oh my gosh. HCl, come on, to water. Water is not a buffer, so not a buffer. And if we added HCl to water, what we would see is it would 100% break apart into our H plus and Cl minus. And what we have done is just made a lot, means the concentration of H plus. So for example, let's just say that our water started at a pH of 7. After you add it, maybe it goes to like a pH of 2 or 1, a very big jump, say, in the pH of that solution. And that's because we produce a lot of free H plus very, very fast. If we look when we add something like sodium hydroxide, which is a strong base, to that solution of water, it would break up into Na plus and OH minus, which means we just produced a lot of free OH minus. And what that means is if we made a lot of OH minus, the amount of H plus would go down, and vice versa, the pH would go up in this particular case. And we would see perhaps in this case, the pH of that water, say it started at 7, would end up at like a pH of 12, 13, something like that. A pretty big jump in pH because we produce a lot of OH minus very quickly. That production of that OH minus decreased the amount of H plus, and we see a big jump in pH. So when you add a strong acid or base to a non-buffer situation, you're going to get big jumps in pH because essentially you're producing a lot of free H plus and a lot of free OH minus relatively quickly. Now let's look what happens when we do add the same guys to a buffer. We're going to use something like acetic acid and sodium acetate. That is a weak acid and its conjugate base. So the acetic acid is the acid part. The sodium acetate is the base part. And if we take hydrochloric acid and we add it to that buffer, remember both of these things are in the beaker today. And the important part is acetic acid, which was part of the buffer, that's not going to affect the pH. And that was what always happens when you use a little bit of one part of the buffer in a reaction. You actually will make the other part of the buffer. Sodium chloride is a neutral salt. It won't have any effect on the pH. But more importantly, what we do not see on the right-hand side of this equation that we do see above is we see that we did not produce any free H plus like we did over here, right? Wow, that's a big arrow. Yep, there we go. So we produced a lot of free H plus up there. And because we didn't produce any more free H plus, the concentration of H plus is relatively constant. And that means that the pH will remain relatively constant as well. Because remember, it is the free amount of H plus floating around the solution that has a drastic effect on pH. So because in the buffer situation, we didn't produce any more free H plus, the H plus concentration remains relatively constant. And by default, the pH will remain relatively constant. I say relatively constant because, again, if you're monitoring the pH, you will see a slight drop in the pH. So again, maybe it goes from 4.74 where it began to a pH of like 4.6 or something like that. So it maintains about the same pH, but you won't see a big giant jump in pH because we didn't produce any free H plus. Same thing would happen if we added our sodium hydroxide to our buffer. When we do, it would react with the acid part of the buffer, which is this guy. And we'll get an acid-base reaction where we produce sodium acetate and water. And the same thing happens as we see above. We produce this guy, which was part of the buffer to begin with, which means it's not going to affect the pH. But again, most importantly, what we do not see down here on this side is no free OH minus, like we did see up here, right? We saw a lot of free OH minus being made. And because we didn't basically make any more OH minus, what that means is that the concentration of OH minus is constant, which means that the concentration of H plus should remain relatively constant. And what that means is the pH should also remain relatively constant. So essentially how a buffer works is because it has both a weak acid and a conjugate base, or a weak base and a conjugate acid, it basically has both an acid part and a base part. When you add acid to the buffer, it will use up some of the base part. and makes more of the acid part of the buffer. But most importantly, when you add an acid, you will not produce free H+. And because the overall concentration of H+ in that solution remains constant, the pH will remain relatively constant as well. And same thing with the base in the buffer. When you add the base to the buffer, it will use up some of the acid part and make some of the base part of the buffer. So what happens is we do not produce any more free OH minus, and because the concentration of OH minus remains relatively constant, so does the pH in that case, because the OH minus and the H plus are tied together. And just to visually kind of show you what's sort of happening, again, if this cooperates, hopefully for a half a second here. If we had a buffer, maybe if we had a buffer, come down. And again, it has an acid part. I'll just call it AP. It's not cooperating. And it also has a base part called BP. And this is our buffer. Now, when we take an acid and we add it to our buffer, it is going to react with the base part of the buffer. And what's going to happen is the acid part of the buffer will get bigger. A little exaggeration drawing. The base part of the buffer will get the part of the buffer. And what will happen is the base part of the buffer will get bigger. And the acid part of the, and the overall way that it's able to basically work is because it has both of those things in the solution, the acid part and the base part for the buffer. When you add acid, the base part takes care of any H plus that would normally come into the solution. When you add a base to the buffer, the acid part takes care of any OH minus that would normally come into solution. And basically, it's able to maintain both the H plus concentration and the OH minus concentration as being relatively constant. And what that means is your pH remains relatively constant. It also means that buffers do have a buffer capacity, which means, let's say, for example, you didn't read the instructions, which I'm sure would never happen to anybody here. But let's just say you grabbed off the shelf like the 18 molar hydrochloric acid instead of like the 0.1 molar. Or you didn't read the instructions and you just kept adding acid and adding acid. What would eventually happen is if you kept adding acid to the buffer, the base part of the buffer would continuously get smaller and smaller and smaller until at some point you really won't have a base part of the buffer still left. And at that point, if you continuously add acid, it would no longer be a buffer. And you would actually see a big change in pH at that point because you kind of blew through the buffer's capacity. So the molarity of what you're adding in terms of strong acid or strong base to the buffer, the molarity of the buffer itself is really important for how effective a buffer can be. But again, you can see just in this picture, if you just went crazy and just kept adding acid, at some point you'll blow right through the buffer part of the base part of the buffer, and it would no longer be able to maintain basically a buffer. Any questions on buffers? Okay. So that actually does conclude this chapter, I think. And the lab today is acid and bases, so it's all about pH, buffers, and all that. Remember, really, here's a table of the characteristics of buffers. It does need to be a weak acid or conjugate base, or a weak base and its conjugate acid. But basically, it will resist changes in pH. Again, it does not mean that a buffer solution is always going to be neutral, like a pH of 7. You could have a buffer at any pH, like we talked about. But what it does mean is whatever pH it starts at, it should be able to maintain that pH very close to it, even if you add acid or base to it. But that's a slide I think somebody wanted me to go back for, I hope. Let's talk about what's left. So today's lab is acid and basis, which will be up there as soon as we're done here. It will be due today, so make sure you do turn it in. We'll take a break like normal, and then we'll start up the lab session in case you have any questions or anything like that. A reminder that the exam has been moved from this Wednesday to Monday of next week. So that'll give you a whole week to digest chapter 16 as well. The exam will cover chapters 14, 15, and 16 since we moved 14 off of the last exam. The homework will also be due on Monday. I don't think I've had a chance to change it, but I will change it until next week as well. But it will also be due around Monday as well. What that means is I think what we're going to do is we're going to move up the experiment from next Monday to Wednesday. So we will be doing the, I think it's the Chatelier's principle, which we will hopefully talk about obviously on Wednesday during lecture, which is chapter 17. And those notes again should be up online. And it is our very last chapter. Yeah, when it's all done, I think after that. So we got chapter 17 will start on Wednesday. We'll move the Le Chatelier's principle up until this coming Wednesday, I think. And then we will take the exam on Monday. We have one more lecture, I think, the following Wednesday, or review or whatever we'll do on that day. And then I think our final should be the following week, I think. So we're getting to the end here, I think, in terms of everything. Any questions on anything? It's a good question. I have no idea, to be honest with you. I'm assuming they'll just check you out. You're all good, I suppose. And for the most part, I think if you come back to campus at some point, they will most likely give you a new goggle and lab coat, since they usually give you that every semester anyways when you start. My guess is you're good in terms of checking out. I would be my guess. I haven't heard anything official on that. I'm sure at some point I will hear. I'm still not sure if you broke something, if they're still going to charge you or not, for that stuff that maybe you broke, before we were left campus and stuff like that. So I'm not sure about that aspect of it. But physically checking out of the lockers, I'm pretty sure you don't have to worry about physically checking out in terms of the lockers and stuff like that. So I haven't really heard anything in particular about that, but I'm sure I might as well. But in terms of if you did break something, you may still see the charge appear at the end of the semester, or you may not. Again, I don't know what their plan is on that, to be honest with you. Other questions on anything like that, or what's coming up in our last, I guess, 1, 2, 3 weeks, and then we're done. Yeah. All right, so we'll take a break. So maybe like 12:10, 12:15, I'll start up the lab one in case you have lectures, in case you have questions. And I think based on everything we talked about through buffers here, you should hopefully be able to answer anything. But if you do have questions, feel free to pop in and ask your questions. The lab's not up yet, so as soon as I'm done here, I'll go click it on, and then you should be able to do it. I think it's 3 videos for each of the parts of the experiment, and then some calculations like pH calculations and H+ calculations. And again, you will hit a -1, I think, on the post lab. Maybe on both of them, you may hit a -1 on the last 2 post lab questions, if I'm not mistaken, in terms of pH. All right, any questions on anything? All right, I'll see everybody in about 12:10, 12:15 for the lab if you have questions. Otherwise, the lab will be up in about a minute or two, so you could start it when you're ready.